What is quantum computing? Why should I care about it? And how can I learn more about it in just 10 minutes? Well, you've come to the right place. Let's do this. So let's start off with a quick recap of classical computing. We all know that a computer stores information in bits. A bit is basically a tiny memory cell that can store either a 0 or a 1. To represent these values, computers use some physical phenomena. For example, transistors that can be turned on or off, capacitors that can be charged or not charged, magnetic spins that point up or down, and so on. This approach works great, but there are some problems. One problem is that turning something on or off, or putting something into a charged or uncharged state, requires energy. So the first challenge is that we would like to find states that require very little energy to maintain. The second challenge is that if you have two bits that are close to each other, they might influence each other and flip their values without you wanting them to. This sounds bad, but we actually use this effect in modern electronics to implement logic gates like and or not. But this also means that the physical implementation of bits, for example, the magnetic spin that points up or down, must be larger than the quantum of something. What does that mean? Well, imagine you have a box. If I ask you what's inside, you might say a cat, or a dog, or a mouse. But what if I told you that there's exactly one thing in the box, but I didn't tell you what it is? Now you might guess that it is probably a small object like a mouse, because it would make sense to put something like a couch in such a small box? This idea is called the uncertainty principle from quantum mechanics. Basically, the more precisely you know one property of an object, the less you know about another property. In our case, the size of the box and the mass of the object inside. So, if the box is small, then the object must be small too. Now, we had this problem already when we were talking about magnetic spins that could point up or down. The issue is that these spins need to be large enough to distinguish them from each other. Otherwise, they will interact and flip their values. However, large spins require a lot of energy to turn them around. And they are also expensive to manufacture. So the question is, how can we store bits that are small and don't require much energy? Well, here quantum mechanics comes to the rescue. In quantum mechanics, everything is both a particle and a wave at the same time. It is just that. Under everyday circumstances, we do on it notice the wave properties of matter, because they are way too small to measure. But quantum bits, qubits, exploit this property. Qubits are not just particles like you and I. They're also waves spread out over space. This means that a qubit can exist in several places at once. And since it's a wave, we can superpose the different locations. So while a classical bit is either here or there, a quantum bit can be here and there at the same time. The reason why this is useful is that we can use these superpositions to perform calculations faster. For example, if we want to multiply two numbers, there's a simple algorithm for that, but it takes a lot of time. For example, for two 5-digit numbers, it takes about 100 steps. Quantum algorithms, however, can take significantly fewer steps. Schur's algorithm, for example, which was discovered by Peter Shor in 1994, can calculate the product of two large numbers in polynomial time. This means that the number of steps it takes grows roughly proportionally to the logarithm of the number of digits. So 4 to 5-digit numbers, it only takes 300 steps. Sounds good, right? But quantum computers are not just about doing math faster. They can also simulate other quantum systems. For example, molecules or materials, molecular dynamics. For example, govern how molecules move and interact, which is important to understand in chemistry and biology. These dynamics can be quite complex and hard to analyze. So a quantum computer that simulates these dynamics could help us develop new drugs or materials faster. That all sounds pretty good, but there's one major problem. We don't have a quantum computer yet. There are some prototypes, but they are still very small and so most of the things I've told you so far are not really practical yet. We are still in the research phase. Now, you might think that quantum mechanics is weird and counterintuitive. And that's true. But I want to convince you that the ideas behind quantum mechanics are actually not all that crazy. They are based on simple observations The first observation is that the world is made of waves. When we talk about sound waves or light waves, we always assume that these waves are traveling through something, for example, air or a string. But waves can also describe the behavior of objects. Light waves, for example, exhibit wave properties, even though they are made of particles. Similarly, particles like electrons can also display wave properties. The second observation is that all these waves interfere with each other. The famous double-slit experiment shows this clearly. If we shoot electrons one at a time at a screen with two slits in it, they form an interference pattern on the back wall. This shows that each electron went through both slits at the same time. The final observation is that these waves collapse when we try to measure them. This means that if we try to look where the electron went, it suddenly stops acting like a wave and just goes through one slit or the other. If you think that this doesn't make any sense, then you're not alone. Einstein called this the ghost of a physical quantity that was supposedly measured, but maybe it makes sense after all. The issue with quantum mechanics is that it is counterintuitive because we are used to thinking in terms of we think that objects go from one place to another along some path. But maybe this is just because we have never seen objects smaller than atoms going from one place to another. We have no idea what the paths of these objects might look like, so it might very well be that there are no paths at all. It might be that they just exist in many places at once. So what is quantum computing? It has basically the idea that we can use these weird quantum properties of matter to speed up calculations. It is kind of like we have a big box of Legos and we can build anything we want with them. Only now we have new types of Legos. Those are the qubits. They're both particles and waves and they can interfere with each other. So now we can build new cool stuff with them. Okay, now that you know what quantum computing is, you might want to know how you can learn more about it. But there are so many courses online. How do you know which ones are good? I've taken a few courses myself, and I found that Brilliant is really great because it gives you a feeling for what's going on. For example, their course on quantum computing starts out by explaining the basics of interference and superposition. Then you get to play around with these concepts in interactive simulations. Later, you'll learn about entanglement and the uncertainty principle. And finally, you'll learn how all this can be used to perform calculations. I really like this approach because it gives you a feeling for what's going on and lets you play around with the concepts before you get too deep into them. Also, it turns out that understanding quantum mechanics helps in other areas of science too. For example, I recently read a paper that used quantum mechanics to explain how life came about. I thought that was fascinating, and I learned about this through Brilliant's course on scientific thinking. It's amazing how many areas of science can be understood better with quantum mechanics. I hope you enjoyed this 10-minute introduction to quantum computing. And if you want to learn more about it, check out Brilliant. Thanks for watching. See you next time!